our pressure volume loop, and what I wanted to do is kind of explore this a little bit further. And kind of a nice place to start might be with the name, right? Pressure volume, or PV loop. And part of it makes perfect sense. You got P there and you got V there, so there's your PV. And the loop, one loop in this kind of sense, is really going to represent one heartbeat, right? So you're going to start at one point and kind of go all the way around from systole and diastole and back. And so using our PV loop, the one that we kind of drew together, let's actually show where systole would be. So if this is kind of where we start, the red represents all of systole, kind of going on and on. And this part is really quick, right? Just a fraction of a second, 0.05 seconds. And then finally, the aortic valve pops open and systole continues. It's not like it just started there, right? Systole starts with the initial contraction of the left ventricle, continues through all of this, and also on this part where the pressure is falling. That's all systole. In fact, let me label that very clearly so it's clear that the red part is systole. And then that leaves, of course, another whole half of our loop, although in terms of time, much more than half, right? Because some of these segments take longer. I'm going to do all this in blue, and all of this stuff in blue represents diastole, kind of the other half of the heart cycle. So this is when the left ventricle is now relaxing. So this is systole and diastole. You can see kind of next to each other on this graph. So this represents one loop or one heartbeat. So sometimes you hear phrases. You'll hear the phrase end diastolic such and such, or end systolic such and such. So what do they mean? Well, end diastolic is literally what it sounds like. It's the end of diastole, kind of where I drew an arrow. And what they're really talking about is a time point, right? So at that point in time where diastole is done, you have a certain pressure, or sometimes they'll talk about end diastolic volume. So I'm just going to write or. But these two terms, end diastolic pressure or end diastolic volume, are really referring to a time point where diastole has come to an end. I guess you could also say start systolic, right? And that's kind of the same idea, right? That's where systole is also beginning, where diastole is ending. But you don't really hear that term. You usually just hear the term end diastolic. In fact, I think start systolic is a word I might have just made up. So let me actually just erase that. But I do want to point out that the concept would be the same, right? It's just a certain time point. So end diastolic pressure volume is that point in time. And at that point in time, just remember a few things are happening, right? You've got, for example, the mitral valve just closed. So I'm going to write mitral closed. And if the mitral valve is closing, also means the tricuspid is closing. And of course, I'm going to put it in parentheses because this is the pressure volume loop for the left ventricle. So really, we're not really thinking about the right ventricle, but some of the events are going to be the same, right? So the tricuspid is going to close at this point as well. And if the mitral and tricuspid are closing, you know they're going to make a noise. They don't close silently, right? And that noise we call the first heart sound, or S1. And if you think more along the lines of what it might sound like, we always kind of think of the idea of lub. You know that sound of lub-dub? Well, the lub part of it comes from the closing, and now you can see on this loop where that might happen. Now on the other side, you've got kind of a similar set of stuff going on. So you've got what we call end systolic, right? So if there's end diastolic, you better believe there's going to be end systolic. And this is going to be, again, pressure or volume. So the pressure volume part gets kind of confusing, but just remember what people mean when they say end systolic. All they're trying to get at is that point in time. And just as before, you could pretend to make up a term, I suppose. You could say, well, isn't that the same as start diastolic? And I suppose you'd be right. But because no one uses it, again, I'm writing it out just to kind of prove the point, but I'm going to erase it so you don't get confused, because end systolic is kind of the term everyone has kind of come to adopt. Now, certain events are happening here too. You've got the aortic valve closing, right? So this is a closing of a valve. And you've also got, although not here, you've got the pulmonary valve closing. So you could also say, isn't the pulmonary valve closing? And the answer is yes. And these two together make a noise, of course. I'm going to write right here, S2. and this is the dub noise. When we hear lub-dub, now you can see where the dub part comes from. It comes from that second point on our loop. So we've got a couple points on our loop, and these loops are used all the time. In fact, kind of the main reason we use these loops is because they convey so much information very, very quickly. So for example, let me just kind of show you why we might use these loops or how they're useful to you by showing you some of the information you can glean from them. So you can actually, for example, take a look at these two numbers and you'll say, well, what is that? Well, this is your pulse pressure. Now you might have heard pulse pressure before, and usually the way we think of pulse pressure is if someone says, hey, your blood pressure, Rishi, your blood pressure is I'm going to make this up, 130 over 80. Well, I would say, well, my pulse pressure is just that means that my pulse pressure is just the two numbers subtracted by each other, right? So it would be, pulse pressure would be 130 minus 80, or 50, right? So this is just kind of an example, right? So this would be pulse pressure, kind of the way we usually think of pulse pressure, just your systolic pressure minus your diastolic pressure. But looking at your PV loop, remember this is not your aortic pressure, which is what we measure usually in your arm. This is actually your left ventricular pressure, right? So left ventricular pressure is going to be very, very similar. You've got kind of the low end right here, and you've got the high end. And the low end is really the lowest that the blood pressure in the aorta is going to be, and the high end is the highest that the aortic pressure is going to be. So your pulse pressure you can kind of figure out using this loop. I would say, well, on this loop, the pulse pressure equals 120, because that's the high end right there, minus 80. And so I would say my pulse pressure equals 40 millimeters of mercury. That would be my answer if someone asked me, what is the pulse pressure on this PV loop? So the cool thing is that you can actually use these PV loops to calculate things like pulse pressure. Now, another interesting thing you can quickly calculate is this. I'm going to just kind of draw it with green, a different color. And this is my stroke volume. Stroke volume. All that means is the volume of blood that leaves my heart with every stroke, right? So you've got at the one end, when my left ventricle is really full, you've got 125. And then when it finally kind of squeezes as much as it's going to, you end up with 50. So my stroke volume is literally just 125 minus 50, and that ends up being 75. So if someone said, hey, what's your stroke volume here? I would say, well, it's 75 milliliters. So one final thing then, I don't want to kind of overwhelm you, but I want to really point out all the kind of interesting things you can learn from this PV loop, is what we call the ejection fraction. Now this is just the stroke volume, which we just calculated to be 75, right? Divided by what they call peak volume, or total volume in the left ventricle when it's full. I'm going to call it peak volume. So in this case, what is the peak volume? Well, it's 125, right? That was the highest amount of blood that we got into this left ventricle. So the ejection fraction would be 75 divided by 125. And notice that the volumes cancel, right? So all you're left with is just two numbers over each other. And in this case, you get 60%. I'm writing it as a percent. You could also say it's 0.6 or 0.6. But usually we talk about it in percentages. So I would say the ejection fraction using this PV loop is 60%. So you can look at these PV loops and you can learn certain words like end diastolic, end systolic. You can calculate things like your pulse pressure, your stroke volume, or ejection fraction. So they basically give you a ton of information, and that's why we always use them.